In this video, we're going to continue looking at section 4.2, and we're going to talk about sigma notation, which will be an important tool for how we add up lots of things very quickly. We saw in the last video finding areas of maybe 5 rectangles or so and adding those up. That wasn't a huge deal, but it wouldn't really be practical to make you do that with 20 rectangles or 50 rectangles or 1,000 rectangles. We need some shortcut ways of dealing with this. Back in Algebra 2, you talked about sigma notation, which is some notation that lets us add things up. You probably didn't see this in pre-calc because things were kind of weird last spring. So I'm going to make this video a little more explicit than I usually do when I teach this stuff in calculus, because you don't have last year to lean back on. But hopefully, these ideas will come back from Algebra 2. To get us started, I'm going to write this Greek letter, sigma. Below it, I'm going to say I equals 1. Above it, I'm going to say 4. And inside it, I'm going to write I squared. This sigma means sum. I'm going to be adding up a lot of things. This I squared is my formula for each term in my sum. This I equals 1 is my lower limit, and this is the first number you're going to plug in for I. And then you're going to continue plugging in natural numbers until you reach this upper limit of 4. I'm going to plug in 1, and I'm going to get 1 squared. I'm going to plug in 2, and I'm going to get 2 squared. I'm going to plug in 3, I'm going to get 3 squared. And I'm going to plug in 4, my upper limit, and get 4 squared. I need to add these 4 problems together. So this sigma formula really gives us the problem 1 squared plus 2 squared plus 3 squared plus 4 squared. Well, that's 1 plus 4 plus 9 plus 16. You're going to add those up, and you're going to get 30 from that. I can read this as the sum as I goes from 1 to 4 of I squared, and that sum equals 30. Let me show you another one. Let's say we have the sum as I goes from 3 to 5 of 6i minus 3. What's the first number that I need to plug into this formula for I? Well, should just be our lower limit. I'm going to go and I'm going to plug in 3, and I'm going to get 6 times 3 minus 3. Then, you're going to keep plugging in numbers until the last number you plug in is what? Should be that upper limit. So I'm going to go and I'm going to plug in 4. 6 times 4 minus 3. I'm going to plug in 5. 6 times 5 minus 3. And I'm done. You go finish this off, just work through the arithmetic, and tell me what this sum equals. Okay, so this is 18 minus 3, plus 24 minus 3, plus 30 minus 3. This is giving me 15, plus 21, plus 27, which should be 63. This sum equals 63. I want you to try the next one on your own. I would like you to do the sum as I goes from 2 to 4 of 20 minus I squared. You see what you can do. Plug in 2, plug in 3, plug in 4. This is going to give me 20 minus 4 plus 20 minus 9 plus 20 minus 16. This is 16 plus 11 plus 4. 20 plus 11 should give you 31. That sum should equal 31. Now, it's not super practical for me to ask you to do this as I goes from 2 to like 500. You'd have to write out all those terms. So as we move through this video, we're going to learn some shortcuts for dealing with those things. But the next thing that I'd like to look at is writing series in sigma notation. Writing series in sigma notation. Kind of taking the answer and creating the sigma from that. For example, let's take a look at the sum. 4 times 1 cubed minus 5 plus 4 times 2 cubed minus 5 plus 4 times 3 cubed minus 5 plus dot 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 plus 4 times 22 cubed minus 5. Please copy that down. So I want to write this in sigma notation. And the first thing I'm going to have to do is I'm going to have to look at these problems and try to notice what is changing. Every single one of these problems has a 4 in it, has a cube in it, and has a minus 5 in it. And the only thing that's changing is what I'm cubing. I'm cubing 1, I'm cubing 2, I'm cubing 3, and so on until I cube 22. That thing that's changing, that's going to be my variable in sigma notation. I'm going to make my variable I, so it's usually the number we use. Looks like the first number I plugged in is 1, and the last number I plugged in is 22. So I'm going to make my series, the sum, as I goes from 1 to 22 of. Every term has a 4 times. Every term has your variable getting cubed, so I cubed, and every term has a minus 5. This is your formula in sigma notation. I'm noticing what's changing. I'm making that thing my variable, and I notice I first plugged in 1 and I last plugged in 22. I want you to try one now. The sine of 2 times 4 plus 6 plus the sine of 2 times 5 plus 6 plus the sine of 2 times 6 plus 6 plus dot 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 plus the sine of 2 times 20 plus 6. Get it copied down and see if you can write this in sigma notation. Let's see, plug in 4, 5, 6, up to 20. I'm going to make my variable I equals 4 to 20. This is going to be the sine of 2I plus 6, because every term has a sine in it. Every term has a 2 times in it. Every term has, well, that number that's changing, 4, 5, 6, and so on. And every term has a plus 6 in there. That should be your final answer for this problem. We're now going to look at a few that are a little bit tougher, but more along the lines of what we're going to end up dealing with to do our area approximations. For the next one, 3 over n times, you know what, I'm just going to write, you write, and I'll make this pause once I'm done writing this thing down. It's going to be a little lengthy. Okay, get that copy down and we'll talk about the sigma together. Okay, there's a lot going on here, including that extra variable, n. Well, even though there's a lot going on here, every term has a 3 over n in it. Every term has a 4 times something over n cubed. But that thing we're multiplying the 4 by is changing. Every term has a 3 times something over n squared. We're just, again, changing what we're multiplying that by. And I think that's going to do it. Looks like the first number I plugged in was a 1, and then a 2, and then a 3. And I kept plugging in numbers until I plugged in, okay, this is weird, but this is kind of where we're going with this stuff. I have an n for my upper limit. This is going to look like the sum as I goes from 1 to n. Every term has a 3 over n in it. And then, looks like 4 times my variable. N is not a variable, n is a constant. We're going to say 4i over n. I'm going to cube that. And I'm going to add to that 3i over n, which I'm going to square. Again, every term has a 3 over n in it. Every term has a 4 times my variable over n cubed. 4 times my variable over n cubed. Every term has a 3 times my variable over n squared. And I'm going from 1 to n. I'm going to give you one, and I'd like to see if you can write this one in sigma notation. Okay, go for it and see if you can write that in sigma notation. So, looks to me like the only thing that's changing is this number over here, 1, 2, 3, and so on up to n. So I'm going to make that my variable. I'm going to do the sum as I goes from 1 to n of 5 over n times 6 times 1 minus 3i over n, and I'm going to square that. And that should be my sum. Next, to be able to evaluate these things, or really any sort of sum that will, be beyond what we can just write out and add up all the terms, we need some properties of sigma notation, and then we need 4 special sums. Properties of sigma notation. First, if I want to do the sum as I goes from 1 to n of k times a sub I. We usually write a sub I as our formula for the thing that's inside our sigma. Technically, it's a sequence formula because we're figuring out all the terms of a sequence and then adding them up to make them a series. I can take that constant and I can move it out front. I can say k times the sum as I goes from 1 to n of a sub I. I have a second property that says if inside your sigma you have a sum of 2 different sequence formulas, a sub I plus b sub I, we can split this into 2 different sigmas. I can say that's the sum as I goes from 1 to n of a sub I plus the sum as I goes from 1 to n of b sub I. Get those 2 properties down, please. I'm going to combine this with a few special sums. Let's see, you know what, I'm going to start a new page. 4 special sums. Actually, you know what? Give me one moment. Never mind. I'll skip that. For special sum, the sum as I goes from 1 to n of some constant c. The sum as I goes from 1 to n of some constant c. So for example, let's say I want to do the sum as I goes from 1 to 5 of the constant 4. This is asking us, plug 1 into this formula. Well, there's nowhere to plug it in, you just get 4. Plug 2 into the formula, you just get 4. Plug in 3, you get 4. Plug in 4, you get 4. Plug in 5, you get 4. I got that constant 4, and I got 5 of them. Rather than doing this problem, how about I just do 4 times 5 and get 20? If I want to do the sum as I goes from 1 to n of some constant c, I can just do that constant times the number of those constants that I have. And if you're plugging in 1, 2, 3, up to n, there will be n of those constants. The sum as I goes from 1 to n of a constant is that constant times n. Number 2, the sum as I goes from 1 to n of I. For example, the sum as I goes from 1 to 100 of I. Well, what this sum means is plug in 1, you get 1. Plug in 2, you get 2. Plug in 3, you get 3. Plug in 4, you get 4. And we're going to do this for a long time. And then we're going to plug in 97, we're going to plug in 98, we're going to plug in 99, we're going to plug in 100, and we're going to stop. There is actually a story behind this one. There was a famous mathematician named Gauss, who was very good at math even when he was just, a little kid. And, this was a little bit of a problem in school because he was so far ahead of his classmates, and the teacher couldn't really get to the other classmates because he was, trying to, push things along and move things faster. So at one point, Gauss's teacher said to him, I want you to sit down and tell me what 1 plus 2 plus 3 plus 4 up to 100 is. And the teacher figured, well, she could get, about a half an hour work out of him or something like that. He looked at the problem, came back to her 30 seconds later with an answer. Here's what he did. He didn't do 1 plus 2, get 3, and then plus 3, got 6, plus 4, get 10, and so on. He did it like this. He added up 1 and 100, and that got him 101. He then added up 2 and 99, which gave him 101. He added up 3 and 98 and got 101, and he's going to keep getting 101 for all these pairs. Now, if you're adding up all these numbers, how many pairs will there be? There are going to be 50 of them. This is going to be 50 times that sum we were getting, or, I just want to check this to make sure I don't say something wrong in here. Yep, that's exactly what I thought, 5,050. The way we can generalize this is I can add my first number, well, that's just going to be 1, with my last number, that's going to be n. 1 plus n. I then just have to multiply by the number of pairs. Well, if there are n numbers, there were 100 numbers over here, there were 50 pairs. If there are n numbers, that's going to be n over 2. And the usual way we write this is n times n plus 1 over 2. Make sure both of those are in your notes, please. Okay, and actually, hold on one second. I'm going to open a window to make it a little bit brighter in here. Maybe a little better. Okay, the next one. The sum, as I goes from 1 to n of I squared. For example, the sum as I goes from 1 to 5 of I squared is going to be the problem 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. I don't have a great story from this. I'm just going to show you the formula. We don't really have time to get into where this one comes from. But it's going to be n times n plus 1 times 2n plus 1 over 6. which means if I want to try to figure out this series without actually writing out all those terms and adding them up, I could use this formula that says I'm going to plug in n, that upper limit, 5, times 5 plus 1, times 2 times 5 plus 1, over 6. This is going to give me 5 times 6 times 11 over 6, which should give me an answer of 55, which I believe is the same thing you would get if you actually did 1 plus 4 plus 9 plus 16 plus 25. One more formula. The sum as I goes from 1 to n of I cubed. 1 cubed plus 2 cubed plus 3 cubed up to n cubed. The formula is n squared times n plus 1 squared over 4. I would like to see if you can use that formula to quickly figure out the sum as I goes from 1 to 6 of I cubed. According to my formula, this is 6 squared times 6 plus 1 squared over 4. Oh, by the way, I didn't say this before, but yeah, you're absolutely welcome to use your calculator on these things. Probably should have said that to you earlier. This is 36 times 49 over 4. Go to the calculator. Going to give you 441 for that. We're going to need to be able to work with these 4 formulas. I think I want to just rewrite them all in one place. If you were in class right now, I'd have a big poster of these hanging on the board. These are not formulas you're going to have to memorize. You will be given them anytime you need them. But we do need to be able to work with them. So I'm going to write them down one more time. Please get them sort of in a consolidated form in your notes. Okay, again, please just get those in your notes all in one place, in an easy place for you to refer to, because you're going to want to come back to them frequently. Okay, so I want to show you a couple problems that will make use of these formulas. First one I want to do. I want to do the sum as I goes from 1 to 30 of I minus 1 squared. Plug in 1, plug in 2, plug in 3, all the way up to 30. I do not want to do that. I want to try to use those shortcut formulas to get me there. But the first thing I need to do is this is not really just one of those formulas. This isn't just a constant or a variable squared or a variable cubed. It's a little more involved. I need to use some algebra to rewrite this thing. First thing I need to do is I need to go FOIL I minus 1 and I minus 1. Whoops, got that wrong. I minus 1 times I minus 1. And when you do that, you get the sum as I goes from 1 to 30 of I squared minus 2I plus 1. This is looking a little bit better. But to be able to use my formulas, I'm going to take a moment and use my 2 properties to rewrite this as 3 different sigmas. I can say that this is the sum as I goes from 1 to 30 of I squared minus, I can move that constant out front, 2 times the sum as I goes from 1 to 30 of I plus, that's just a constant, I'll leave that as a constant, the sum as I goes from 1 to 30 of just the constant 1. And the point is, now I have 3 sigmas that I can evaluate using the formulas that I just gave you. So, to do the sum as I goes from 1 to 30 of I squared, I'm going to plug 30 into my I squared formula. I'm going to get 30 times 30 plus 1 times 2 times 30 plus 1 over 6. I'll figure that out in a moment. Then I'm going to do minus 2 times, well, the sum as I goes from 1 to 30 of just I, that's my second formula. That's the one that says 30 times 31 over 2. Plus the sum as I goes from 1 to 30 of the constant 1, 1 plus 1 plus 1 plus 1, 30 times. Well, that's my first formula. That's that 1 times 30. You take a moment, work through the calculations on your calculator, and give me an answer. Let's see here. 30 times 31 times 61 over 6. I'm getting 9,455. Minus, okay, next part should be 930. Last part should be 30. Add, subtract all that. You should get 8,555. One more of these. The sum as I goes from 1 to n of 1 over n times 2 plus 3i minus 4i squared. Okay, don't panic. I realize this looks a little more complicated. I've got two variables here, n's and i's, and what a mess. My first question for you, though, as far as the sigma is concerned, what's the variable? Is it I or is it n? Well, because we're doing the sum as I goes from 1 to n, I is my variable. N, I'm treating like a constant. You know what? If it's just a constant, how about I move that out front before the entire sigma? And I can make this 1 over n times the sum as I goes from 1 to n of 2 plus 3i minus 4i squared. You take a moment, use your properties, and write the sum as the sum of 3 different sigmas. So I've got my constant 2 plus 3 times the sum as I goes from 1 to n of 3i, nope, sorry, of just I already dealt with the 3 out front, minus 4 times the sum as I goes from 1 to n of I squared. Okay. Well, to evaluate these, plug in 1, plug in 2, plug in 3, up to n. If I go to my constant formula, my constant says it's 2 times the number of terms. Well, how many terms are there? There are n terms. This first thing is really just going to be 2n. As for the second one, what is 1 plus 2 plus 3 plus 4 up to n? Well, it's really just exactly our second formula. The sum as I goes from 1 to n of I is just n times n plus 1 over 2. The last one, the sum as I goes from 1 to n of I squared, is n times n plus 1 times 2n plus 1 over 6. I guess I might as well clean this up a little bit. I can distribute the 1 over n, which really just means cancel this n, cancel that n, cancel that n, and just clean up the numbers a little bit. When I distribute and do that, I'm going to get 2 plus 3 halves times n plus 1, because again, the n's are going to cancel, minus, okay, 4 over 6 is just 2/3. I'm going to say 2/3 times, I'm going to make the n cancel again, n plus 1, 2n plus 1. And I think I'm just going to leave it like that. I think that's going to be good enough for our purposes for right now. There's one last thing we need to look at. And I don't want to go into a whole lot of depth with this, but we need to talk about limits of sequences. Okay, let me get one more piece of paper out. Limits of sequences. Sequences, remember, just patterns. We're going to look at the sequence, S of n. Actually, do I want to do that one first? Yeah, why not? S of n equals 64 over n cubed times n times n plus 1 times 2n plus 1 over 6. Please copy that formula down. This is a formula that can give us a pattern of numbers. For example, if you plug in 1 for n, you find that the first term in the sequence is 64. Plug in 2, you get 40. Plug in 3, you get something messy. We're just going to go with 33.185. Plug in 4, you get 30, and we can keep plugging things in. What I want to figure out is what happens as n, the term in our sequence, gets really big. You plug in 10, you get 24.64. You plug in 100, 21.6544. Plug in 1,000, 21.365344, and so on. And what you should see is these are kind of leveling out. And I want to see, as n gets really, really big, what is this sequence approaching? Well, hopefully that sounds a little bit like a limit to you. All I want to do here is I want to find the limit as n approaches infinity of that sequence formula of S of n. Well, that means I want to do the limit as n approaches infinity of 64 over n cubed times n plus 1 times 2n plus 1 over 6. I'm going to do this exactly the way we did this in Unit 1. This is not written in a great form. Remember, Unit 1, by the way, was the one where we did those limits at infinity by looking at the ratio of the leading terms? Right now, I hope you're saying out loud, yes, I remember that. Wonderful. Problem, though, is this is not in a great form. I need to do some foiling to try to make this work. I'm going to say this is the limit as n approaches infinity, and I'm just going to leave 64 over n cubed like that. I'm going to say n times, okay, I'm going to go FOIL those two things. 2n squared plus 2n plus n plus 1 over 6. I'm going to do a little more algebra with that. I'll combine like terms, make that 3n, and I'm going to go distribute the n, and that gives me limit as n approaches infinity of 64 over n cubed. Deal with that in a moment. 2n cubed plus 3n squared plus n over 6. Now, why don't I distribute that 64 and the n cubed, and I'm going to get the limit as n approaches infinity of 128 n cubed plus, I want to say 196, no, 192, sorry. 192 n squared plus 64n all over 6n cubed. Well, hopefully now you feel like it is in a good form. I can rewrite this as the limit of the ratio of the leading terms. So the limit as n approaches infinity of 128n cubed over 6n cubed. And cancel the n cubes. My limit is 128 over 6, but I can do better than that. I can say my limit is 64 over 3. Right now, all I really care about is that you can go through these calculations. We're going to see later that these calculations are going to help us find the sum of the areas of the rectangles when there aren't 10 or 20 or 50 or 100 or 1,000, but actually when there are infinitely many rectangles that are really, really, really narrow. And that will get us our actual area. We're not going to worry about that right now. We're just going to try to go through these calculations. And realize you're going to get this weird-looking formula. Where does this come from? This is actually going to come from some of our area approximation stuff, but I don't care about that right now. It's just a formula. I need to expand things and write things in expanded form so I can then do the ratio of the leading terms. I would like to see if you can handle, and this will be the last example in this video, I'd like to see if you can handle S of n equals 1 over n squared times n plus 1 over 2 I want you to find and submit to Edpuzzle the limit as n approaches infinity of that sequence formula. Give it a try. Oh, this is so much easier than that last problem. I'm going to get a half. That limit is a half. In the next video, we will do a little bit more work with these sigmas, but then see how we can apply them to our area approximations. And let us deal with 10, 20, 30, 40 rectangles. And then we'll take it a step further. What if we have infinitely many rectangles? And right now, this whole video that you just watched, these are the tools we're going to need to help us get there.